Okay, now I think, yeah, I'm recording. Okay. Hi everyone. Welcome to this session of the One Word Machine Learning Seminar. Today we are very happy to have Pierfrancesco here to give us a talk on his recent work. So Pierfrancesco is now a postdoc at MIT, working with Professor Thomas Poggiu, working on machine learning theory and the mathematics that develops the deep learning and machine learning. And before that, he was a PhD student at Princeton, part of the ORFE department and the machine learning theory group. And he was advised by Professor Boris Honey and Professor Jason Lee. So without further ado, let's enjoy Pierfrancesco's talk. Thank you.
Thank you so much. Thanks a lot. Thanks a lot, Vuyang, and the organizer for allowing me to be here. And good morning and good afternoon or good evening, wherever you are. So I'm Pierre. You can call me Pierre. It's very nice meeting you. And I'm gonna speak today about something that excites me a lot, and is like the edge of stochastic stability. So what is the edge of stochastic stability? Is the generalization of edge of stability to the mini-batch settings, and no worries if you don't know what that is, because I'll say that for the first 10 minutes. And what is that? It's like a surprising, at least to me, precise empirical description of the behavior of mini-batch SGD in vision classification tasks and when trained with mean squared error. So why does it excite me? The reason why it excites me a lot is that I'm a mathematician working on the mathematics of machine learning. And this is, I think, a phenomenon that puzzled and frankly a little humbled theorists and practitioners in a sense in the past 5-10 years. Practitioners were telling us our mathematics didn't work to predict training how to train neural networks or the training dynamics of neural networks, and we were telling them they were wrong. The truth was somehow in the middle, and essentially I think I'll characterize what the truth was during my talk today and with the description that I give. And it's an empirical work. There is a theorem. The theorem is key, but I think the main message is empirical. And it's an empirical characterization of SGD trajectories, which, importantly, I'm a theorist, is useful to theorists, I think. So it's there has been a lot of empirical work. This is the empirical work made by a theorist, hopefully for other theorists. So it's a precise description of training dynamics, I was saying, and their instability. And in a sense, explains explains the observations of SGD goes to flatter solutions, and has key implications for the mathematics about deep learning in general. So first and foremost, I did this work with Arseny Andreev, which was a fellow PhD student at Princeton, and I want to say now because otherwise you rush on this at the end. And let's get started. So let me first say what the edge of stability was and give a brief review of the edge of stability. So I think it's very key. It's I suggest you to watch an old talk by Stan, which was about essentially what was known about this kind of effects before the characterization of Jeremy Cohen et al. 2021, and the talk by Jeremy Cohen that introduces the effect of edge of stability. What is the edge of stability? The edge of stability is an empirical phenomenon about full batch gradient descent, full batch. We're going to do the mini batch part. And essentially, we got different characterization of this phenomenon through the years, through a number of independent works, mostly unaware of each other. And some of the articles in which you see this thing are Xing et al., A Walk with SGD, and then 2 papers by Stan, and the paper by Jeremy Cohen, which gives the name to the phenomenon, and I think more neatly characterizes it, although only for full batch GD. And this phenomenon itself explains a numbers of phenomena that we see and observe in deep learning. Is that's the reason why I think is interesting, but even more is like as of key relevance to the theory. So what is this edge of stability? So you take a classification task, you use MSC, both edge of stability and our work will kind of work also for different tasks and different losses, but this is like the task and the loss in which like the effects are much neater. So across many different architectures and the behavior of the training trajectory obeys like some very simple rule, and the rule is not what you expect. And it is like in this like slides, I want to reference like the talk of Jeremy Cohen above, so that like you connect with those. Okay, and what is this like simple rule which is surprising? You take the largest eigenvalue of the Hessian, you call it sharpness, and you plot it. So you plot there a line, and the line is like a 2 over eta. Eta is the learning rate. Why is this line important? Because like above this line, on a quadratic landscape, gradient descent is unstable. Below this line is stable, right? So it's like if you think of like any optimization theory type analysis of convergence, is like assume the learning rate is smaller than 2 over L. Well, this is the 2 over L line, okay? Well, what these papers observed is that like there are three things, three phenomena, three phases if you want, or two phases. One is progressive sharpening. So there is a first phase in which lambda max of the Hessian, the highest eigenvalue, sharpness, increases. Then there is a phase transition that's then defined as break-even point, in which it deviates from its natural trajectory. And after this phase transition, it stabilizes at the edge of stability. It's how Jeremy defines it. Edge because it's like exactly right above of it, you are unstable. Right below it, you're stable. And the thing is, right above it, you're unstable, but you're stabilizing there. So it's like at the edge of becoming unstable, but you're yet not stable. And the stabilization of the highest eigenvalue is like, it's like very, very interesting. And in particular, it led to some very cool implications for full batch GD. So first of all, the conventional wisdom is you pick a step size which is small, and then stop work. Well, pick a step size that is small. It's like an impossible task because smalls mean small given the size of the Hessian, and the Hessian grows. So it's like this conventional wisdom is like, in a sense, wrong when you apply it to training neural network. Also, that you have to go deeper than order to Taylor approximation when dealing with neural networks, because Taylor to approximation here would tell you, hey, you cross 2 over eta and you diverge. Well, you're not doing it. So there's like higher order term, which is like very key to the training neural networks. And like also like convex optimization type convergence analysis do not apply. Like, think about it. You do descent lemma. Well, descent lemma tells you that the loss after one step is right bigger than the loss the step before. This is not the case. So it's like this descent lemma kind of arguments don't apply here. And also that like essentially you want to use GD in certain settings from convex optimization. Also on convex optimization, we know what to use it. And when the step size is small enough, otherwise you use some higher order technique. Well, here GD, like you're not in a setting in which you would like to use GD. The loss indeed does not decrease monotonically. The gradient size increases. I won't touch upon this because I have no time, but it's like the gradient size increases, still GD is successful. So it's like this is also surprising on its own, right? So what are the implications? The implication is that like we like thanks to this edge of stability line of work, now we know in what way location of convergence acclimates to hyperparameters. And this way is about some sort of instability. Is about like progressive sharpening plus instability things. And and there's like sorry. And there's like, and also like the big implication for theoreticians is that like the general optimization theory type analysis like does not apply to GD training. Okay, very cool. So let's see if like what's going on for mini batch algorithms. Well, for mini batch algorithm, everything was kind of open. Like if you think about it, this is like simply not the case for SGD, is it? Like we all read thousands of words about SGD finds flatter minima, and I'm guilty of. I I like worked on at least two of them, and and in particular the like all this work stems by empirical work, which was showing in particular the lambda max of the Hessian, the highest eigenvalue, is smaller than 2 over eta for SGD, right? So it's like, wait, this may not be the case for SGD, so this may be a very cool thing, like gradient descent. Like analysis doesn't work on gradient descent, but not for SGD, and this would be an amazing news. Well, it's a good news anyways, if you characterize that it doesn't work and if you characterize that it's work. But still, and also like all those like implications that we had, like now they're not real anymore, given that like lambda max is smaller than 2 over eta, right? The thing is, actually, like even Jeremy Cohen and co-authors like comment about it in their Edge of Stability paper. And what they comment on is that like progressive sharpening happens. So this is a good news. At least for mini batch SGD, still we know progressive sharpening happens to some sort of extent. That also that location acclimates to hyperparameter, and this is like not a news. We knew it from Kesker again, and like, but like this thing makes it. But all the things is not surprising. Like stuff stay below 2 over eta. And here on the left, you see figure 1 of our paper. And you see that like here, the 2 over eta I didn't plot it, is what was 400. Well, for different batch sizes, and is like monotonic in the batch size, like lambda max flatlines below that. Cool. And also they say, oh, we have like the intuition that edge of stability might generalize somehow to SGD, just in a way that does not center around the sharpness. In extending these findings to SGD, the question arises on how to model stability of SGD. Cool. So it's like, let's see what we know about SGD. So I said it. We know that progressive sharpening happens from then. And also, we know from a paper, very important, I think it's like, in a sense, the paper that like started the implicit regularization effort, Kesker 2026, there's like actually location of convergence for SGD acclimates to hyperparameters in the following way. Smaller batch size leads to flatter model. Smaller batch size leads to better generalization. Okay, and also Kesker observed progressive sharpening. So, okay, we have some hope. Acclimation happens, or progressive sharpening happens, but we even have more hopes that like this acclimation is about stability. Indeed, in like paper of Stan, very relevant, very important, break-even point, Stan and co-authors realize this thing. So you take the like trajectory of gradient flow, you take any trajectory of SGD or gradient descent, and there's a first phase in which they all go together. And we'll see later, as you may imagine, this phase is progressive sharpening. Then happens a phase transition, the break-even point, and the trajectories diverge. What is this break-even point happens earlier for small batch and big steps, and later for big batches and small steps, but could not quantify really where it happens along the trajectory. So, okay, like this like sounds a lot like edge of stability. Essentially, in like maybe like for full batch GD, we said, oh, in what way location of convergence acclimates to hyperparameters, and that this was about progressive sharpening and edge of stability. And like maybe we have some hope to say something similar about SGD. Okay. So without further, like, do people have questions about this so far? This is the turning point. Cool. So without further waiting, I'll get to describe what edge of stochastic stability is. So it's like I already said what that is. It's a surprising, at least to me, precise empirical description of the behavior of mini-batch SGD in vision classification task with MSC. And exactly as now you may imagine, like in what way it responds to this question, given that we understood what edge of stability was. It's like a precise description of the dynamics, their instability or lack of instability. It explains, in a sense, how SGD goes to flatter minima. So the observation we said about before from Kaskar et al. 2016. And it has some key implications for mathematics of deep learning. And they're not just the ones that like edge of stability had, I think a couple more. And we'll speak about it more later. So what is edge of stochastic stability? So take a quantity. This quantity is batch sharpness. This is our quantity. What is batch sharpness? Batch sharpness is essentially the quantity of edge of stability, but on the small batch. So you sample a mini batch B, and now you have your landscape on the mini batch B with your Hessian HB of your mini batch B and your gradients nabla LB on your mini batch B, right? So what is curvature on this landscape? Well, I'm moving in the direction of the gradient. So curvature is the Hessian norm of this gradient. So it's like gradient transpose Hessian gradient. This is like the curvature. There's like, if you want the full batch GD-like curvature in the direction of the step on the mini batch noise, on the mini batch landscape, and like normalized by the size of those gradients. Cool. Like, what does it stand for? Like, can we get like a very natural intuition of what this quantity is? I was like, yes, is this curvature here, and why does it matter? Well, when I write down the descent lemma on the batch, mini batch landscape, well, this quantity smaller than 2 over eta implies that on the mini batch landscape, I'm not going down. That I'm going down, okay? So this quantity is about the same type of edge of stability, but on the mini batch landscape. But now I'm taking an expectation outside of descent lemma, and so I get these two elements, and so what I care is about the ratio of them being not 2 over eta. Okay, so we have an intuition of what this like batch sharpness is, and the observation is the following. Very clear. Batch sharpness stabilizes at 2 over eta. This is MLP setting across different step sizes you see in the different colors and different batch sizes, like smaller to bigger, left to right. Okay, not only like it stabilized 2 over eta very consistently, and this is like if you want a more fine grained plot. So it's like here we have a CNN instead of an MLP. And the blue line is the lambda max of the Hessian, so of the full batch Hessian, and we see that it flatlines too, but lower. Well, batch sharpness always flatlines around this, which is the green line, around this 2 over eta threshold. The red dots, what are the red dots? The red dots are the value of that quantity on each mini batch exactly, okay? So it's it's like at every step I'm sampling a different mini batch. So the red dot is like the level of this quantity on the mini batch that I sampled. The green line is the average over those mini batches. Cool. And also we kind of show that like the stabilization is about batch sharpness, because you may tell me, hey, like maybe something else that stabilizes and leads batch sharpness to stabilize. Well, yes and no. Like when I change the hyperparameters, when I perturb them, I see that like batch sharpness reflatlines. So it's like jumps away or maybe like changes abruptly, but then it restabilizes at 2 over eta. And this is not the case, for example, for lambda max. And this is the wrong picture, but essentially like what you see is that lambda max follows the movement. So it's like whenever batch sharpness is going to 2 over, batch sharpness going to 2 over eta essentially drives the dynamics. Lambda max follows the movement, but acting consistently. It doesn't depend on the hyperparameters directly. For example, it changes a lot given the size of initialization, while batch sharpness doesn't change given the size of the initialization. Cool. So let me describe like quickly and neatly characterize what this edge of stability phenomenon is. So as I said, batch sharpness stabilizes at 2 over eta after a long phase of progressive sharpening. Also, lambda max, so the highest eigenvalue of the full batch Hessian stabilizes, but usually below, and the trajectory is subject of catapults. And this catapult is like, it's very key for me to put this thing. It's like, or at least it's key for theorists to put this like characterization in here. It's like, if you think about it, batch sharpness is the expectation of a quantity. So, and then like actually on every step I'm sampling. So it makes sense that like if I sample like 10 batches in a row for which is above, this explodes, right? In the same fashion in which like if you have lambda max bigger than 2 over eta for full batch GD. And when you do millions of steps, like it's like very unrealistic that like in these millions of steps you don't pick 10 steps which are all above, right? So it's like those like catapults are like part of this effect here. And usually it catapults, it jumps somewhere else in the space and then gets through progressive sharpening and restabilizes. Cool. So this is like the description of edge of stochastic stability phenomenon. And if you remember, we started with the question, hey, what way does location of convergence acclimates to hyperparameters? Is it the machinery inducing it about stability? And do optimization theory type analysis apply to SGD trajectories? Well, in a sense, we answered this question. We got it. We got what the answer is here. It's like, in what way does the location of convergence acclimates to hyperparameters? Is due to batch sharpness empirically. But is the machinery inducing its stability? And in what way does location convergence acclimates to parameters? Is that about batch sharpness mathematically? Okay, so we showed it empirically, but not mathematically. So now by saying in what, if the machinery inducing it is about stability, and will be, we kind of like lock in that batch sharpness is the quantity, and that the effect is of the same kind of the full batch GD edge of stability. So what do we need to show this? Essentially, we need to show, like, we need to have our theorem which says the divergence is implied by batch sharpness being bigger than 2 over eta, and like is not implied by batch sharpness being smaller than 2 over eta, right? But in particular, we like of the two direction, we care more about this one. It's like, if it's implied for 2 over eta, then it means that the level of stabilization is going to be smaller than that, right? That progressive sharpening for the same fashion of edge of stability, we can expect it to stop right before that. Cool. So we get to our theorem. So like I'm not gonna dive into the proof of the theorem because I think the theorem is important to show to you that like what we did is correct, but it's nothing exactly important about the message. Except one message that I'll say right now. So it's like, first of all, you have to define instability. So it's like I'm gonna say, hey, this is essentially as every stability result, if you want, is like about quadratic instability. And it's like, okay, let's take a neighborhood in which I can approximate every one of my small batch landscapes with a quadratic up to a certain approximation error. And we say you experience a catapult if you diverge on this like local quadratic approximation. What does it mean? Well, if you go up but you restabilizes, then it's not a catapult. If you go up and then you go down again, that is not a catapult. I'm going to call it catapult. Essentially, if like you have some sort of quadratic divergence for which you exit every compact set in which this quadratic approximation holds up to a certain threshold, which is going to be constant times eta, okay? Essentially, what we show is that this happens, of course, if like the learning rate is bigger than 2 over lambda max, we knew that. But it happens also when it's smaller, but batch sharpness strictly bigger than 2 over eta plus an absolute constant times eta. Okay, so batch sharpness actually bigger than 2 over eta induces divergence. But very interestingly, and like the reason why this theorem, like it's like a little different than the previous like quadratic stability theorems, is that usually quadratic stability analysis is about you take the parameters, so you take your variables in which you're doing optimization, and you show that the expectation of their norm diverges. Well, if you inspect the expectation of the norm of the parameters, actually you cannot prove that batch sharpness is the quantity that gives you divergence of convergence. You really have to check the variance of the gradients. So like once you check the variance of the mini batch gradients, then batch sharpness show up naturally. So essentially we have divergence if batch sharpness is bigger than 2 over eta, but it's not. It's like it's gonna be a divergence of the parameters too, but it's key that you don't show it through divergence of the parameters. You show it through divergence of the variance of the gradients. Okay, and this aligns with empirical observations that the gradients get bigger. Cool. So essentially, yes, divergence is implied by batch sharpness being bigger than 2 over eta. And so, in a sense, we also said yes to this question. So it's like, is this machinery induced about stability? Yes, we have an answer. And so we got this first part of our goal. Do we have any questions so far? Is everything clear? Cool. So let me move on to what about this question? Okay. Like, what can you say about this thing? And it's like, well, if you think about it, like conventional wisdom about step size is wrong. Still, like you can tell me, okay, but for SGD, then I set the learning rate not smaller than 2 over L, but like smaller than 2 over maximal batch sharpness. Also here, this is an impossible task because batch sharpness is gonna grow because of progressive sharpening. And also here, like you have to go deeper in order to tailor approximation when doing neural network theory. Why? Because like if we assume progressive sharpening, then you're gonna get over batch sharpness equal to over eta, and you're gonna diverge. Quadratic stability gonna tell you that. And this is clearly not the case. So it's like also here we have these two implications. Well, the other two implications are not yet there. So we're gonna try to answer them, but like we're gonna answer them as a byproduct of like discussing like something more in the next chapter, which is why is this even surprising? Right. So it's like, let me tell you a couple words about why this is surprising. Okay, because like what we said, we described a precise empirical description of the behavior of mini batch SGD, which was surprising before knowing of edge of stability. But someone could say, hey, like, okay, cool, but like you described this phenomenon. It was not described, but like it seems very natural, right? Like why is it surprising is a genuine question. It's like edge of stability was surprising, but like seems natural given edge of stability. So in a sense, the question is, if you want, it's like, why did it take 6+ years from the paper A Walk with SGD? Or like, why did it take 4 years from the very neat and clear and nice and clean characterization by Jeremy Cohen et al. Of edge of stability to come up with like this SGD version? Or why that paper was not directly about SGD, right? So I'll try to answer this question now. It seemed very natural, but it actually not. And it's actually not, like, in the sense that like batch sharpness is not the direct of generalization of lambda max from many different point of views that you generally take when you think of stability or convergence. And also like edge of stochastic stability, in a sense, is not the generalization of edge of stability. It's like it reduces to edge of stability, but it's not the generalization of edge of stochastic stability. And we'll say now how it reduces to edge of stability, like not the trivial and natural one. Precisely, by answering this question, we also conclude the implications. Cool. So it's like, in what sense is not the direct generalization? It's like it's not the highest eigenvalue. This is what lambda max was, and this is like maybe it's a very stupid generalization, but still is like the natural one. It's like it's not about descent lemma being stationary. So it's like the reason why it made sense the highest eigenvalue being exactly at 2 over eta was that like descent lemma goes down, tells us we go down. And it's not about this thing. And also like we said, like batch sharpness is about stability on the mini batch landscape, but we're sure that this doesn't imply stability of the overall dynamical system of stochastic gradient descent. And also that is not like I showed you that is about quadratic stability, but it's not this like standard way to approach quadratic stability. Okay, so let me get real quick about how and why this is unexpected. So about the like
Javier, just one
yes,
quick clarification question. What the MB means?
a mini batch. Sorry.
Batch. Okay, yeah. Okay, thanks.
Yeah. Sorry. Cool. So it's like, as I was saying, you would expect, okay, like I'm on the task of generalizing the edge of stability of SGD. Let me see, what do we have? We have the highest eigenvalue of the Hessian. Maybe we can think, like the highest eigenvalue of the Hessian is the average of the highest eigenvalue of the average as the Hessians. Maybe here, like since the average outside, now I have to take the average of the highest eigenvalues of the mini batch Hessians, right? Well, that stabilizes, but that stabilizes above 2 over eta. Unfortunately, this was like our first guess. And also, it has a very interesting pattern. So it's like, it doesn't just stabilize. And this is an open problem. I'm very happy to discuss with anyone about this. And like, it's something that I'm very interested in because it's like, seems very cool and very consistent. It's like, doesn't just stabilize above. So the orange is the average of the highest eigenvalues on the mini batch. The green is batch sharpness, and the blue is lambda max of the full batch Hessian. It actually goes up. So like here on the axis, we're increasing batch size. It's like as you increase batch size, it goes up. It goes up. So this means that like essentially the alignment between gradients and lambda max on the mini batch set landscape is going down. And it goes up until a certain critical batch size where essentially we are in the full batch edge of stability regime. And so lambda max acts like that. And this starts going down. Cool. So it's like, it's very cool. It's a very nice pattern. I have no clue why, but this is not the way to generalize it. Okay. And now let's think of descent lemma. Well, what was this like 2 over eta about? Well, if you write down the descent lemma, essentially you prove that like after one step, you do well in the loss, if and only if a quantity is smaller than 2 over eta, and that quantity is always smaller than lambda max. So it's like makes sense that imposing lambda max smaller than 2 over eta, we also have that quantity taken care of, right? So it's like, this is like the descent lemma point of view on edge of stability. And it's like, now let's try to write down the descent lemma with a mini batch step. So it's like, I want to check the full loss, and I do one step. So I go from parameters theta at the time t to theta at the time t plus 1 with a step on the landscape of the batch red B, okay? So it's like, this is smaller or equal than eta times the gradient of the loss times the gradient of LB, the step, plus eta squared over 2 is like, or like plus 1/2 for the 2 steps which multiply the full batch Hessian, right? Now, this is the descent lemma. In this case, I'm going to take the expectations, okay, and see what's up. And it's like in the same fashion as we did for like full batch GD before. It's like, now we see that the loss decreases on average if and only if like the beat this like essentially doesn't get does get eaten by the expectation in the first term, not in the second term. And so if and only if this quantity is smaller or equal than 2 over eta. And makes sense there is this quantity. Why? Because like if you think about it, for gradient descent full batch, we had like just one direction, and this is gonna align with the eigenvector of the main eigenvalue for GD. But here we have many directions, depends on the batch. So it makes sense that we check alignment and not just like an upper boundary alignment. So this is like the explanation for why this quantity makes sense. Well, this quantity is very different from batch sharpness. Well, in batch sharpness, I'm putting the red B at every possible quantity, right? Here, I'm putting it only at some things. Essentially, in above, I'm looking at the full batch landscape with a mini batch size. Below, I'm looking at the mini batch landscape, right? So it's like batch sharpness is different than here and this quantity. So essentially, like edge of stochastic stability is not the generalization of edge of stability, neither from the highest eigenvalue point of view, neither from the descent lemma stationary point of view. So let's look at the stability of mini batch landscapes. Like the way I introduced batch sharpness was, hey, this is exactly the notion of sharpness, but on the mini batch landscape. And then I take the average, right? Well, so essentially what I'm saying is that batch sharpness smaller than 2 over eta is if and only if the step on the mini batch on the mini batch landscape is stable. The thing is, this does not imply stability of the full batch loss. And why? Because when I take this expectation right there, right outside, and this is an observation that White shoot me by email, and I didn't notice. If you think about it, like you're checking the loss on the same batch on which you did the step. So it's like the step and the loss on which you're checking are correlated. And so this as a second order term, it's not about stability on the full batch landscape. So it's like this like stability on the mini batch landscape is not about stability on the full batch landscape. So it's like it's like it doesn't imply that, right? So it's like it's not even about, like we said, batch sharpness is about stability on the mini batch landscape, but that like is not about stability overall. So it's like even from this, like if you want like dynamical system point of view, is not the generalization we expected. And finally, let's check quadratic stability from a static point of view. So we said, hey, for stable quadratic trajectories, the edge of stability is 2 lambda max equal to over eta. Because lambda max is going to be bigger than that, and that's going to evolve to align with the eigenvector of lambda max. Cool, we got it. What if we have stochastic gradients? Or if you want, you inject noise in the gradients. Well, now you really have to check this quantity here, okay? So it's like, as I was saying, like from the descent lemma, you get this thing. And now you really have to make this expectation, right? But it's like, nothing changes. Like, I'm not gonna, this is like the quantity that, like, I'll define gradient noise interaction later. And this is like the quantity we had before. And even pushing it, so essentially 2 over eta is the stability threshold also for noise injected or stochastic gradients. But if we push this further and we say, hey, the Hessians change. Well, like a very key observation is that when the Hessian change, so like if you want, you have stochastic Hessian, if you want noises injected also in the Hessians, then 2 over eta is not the threshold anymore. But like stable quadratic argument tells us, oh, you're stable if and only if the norm of this quantity is smaller than 1. And this is not, unfortunately, about batch sharpness, right? So it's like essentially, batch sharpness is not even about this quadratic stability in the common sense. So what is this batch sharpness about? So this was the reason why it was unexpected. Now I'll tell you in what sense edge of stochastic stability was a good generalization to edge of stability, except there is real empirically. But okay, in what sense theoretically for mathematician? So batch sharps induces stability. What we needed to show to tell that batch sharp induces stability, if you think about it, is that like batch sharpness was a threshold. So it's like if that divergence is implied by batch sharpness being bigger than 2 over eta. In the case of random Hessians, like by the argument I just said, there's like quadratic are unstable if the thing is bigger than 1, right? And in particular, quadratics are unstable is defined as, and this is the point, the expectation of the norm of the parameters diverge. This is how it's defined, okay? Like, actually, batch sharpness is about quadratic instability, if you want, not about quadratic stability. And like batch sharpness, we said, is bigger than 2 over eta if and only if the second moment of the gradients diverge. So it's like, yes, edge of stability is a generalization of edge of stability from this point of view. And sharpness is about quadratic instability, okay? Not quadratic instability, although they may be the same thing, okay? And so we said why isn't expected. I'll tell you more about what batch sharpness is about. So we said it's about stability on the mini-batch landscape. We said it's about quadratic instability when the noise affects Hessians, and it's very key that the noise has to affect Hessians, okay? And let's go back to descent lemma. Essentially, like when we checked before, like, oh, descent lemma says that loss doesn't go down if and only if this quantity was bigger or smaller or equal than 2 over eta. What does this mean? This means that like loss oscillates if and only if this quantity is smaller or equal than 2 over eta. The thing is, as we know from like implicit regularization, or even for like when you like, if you think about the analysis of Robbins and Moore algorithm, like of like stochastic approximation or any stochastic optimization routine, learning step size decreases, right? You have to annihilate. When step size does not decrease, then there's like we have like a very good characterization of the fact that like you're gonna converge to a stationary distribution, okay, where you have oscillations, but oscillations because of the noise. The stationary distribution is because of the noise. Essentially, this quantity at 2 over eta tells us we are stationary. This quantity at 2 over eta, the quantity we got with descent lemma on the full batch loss in expectation, tells us we have oscillation, but this oscillation could be for noise, like Robbins-Morrow with fixed step size, or could be for curvature, like edge of stability. Like this quantity doesn't tell us why we add this oscillations, right? And we care about the curvature ones. Why do we care only about the curvature ones? Because location of convergence acclimates to the hyperparameter like through the machinery induced by stability instability. So it's like stability instability is induced by sort of curvature. So it's like we care about the curvature ones. And this could be both for noise or for curvature. Also, like as I was saying, like the fact that this stabilizes at 2 over eta is exactly explained by optimization theory type analysis. And so, yes, Robbins-Morrow for fixed step size exactly explained that this thing is going to be at 2 over eta. What we care about is like only the curvature kind of oscillation. So it's like we have to think about it a lot, to be honest. It's like, how do we determine which oscillation are only due to curvature and which are due to noise? Well, turns out, if you think about it, when is it due to curvature? When you're oscillating, the step is oscillating. And essentially, like what we characterized in our paper is that the oscillation that are due to curvature is the ones in which the mini batch loss oscillates and are the ones in which batch sharpness is 2 over eta. All the other ones are due to noise. And in particular, when they're both smaller than 2 over eta, then like convex optimization type convergence analysis applies, and we have like monotonic convergence. When the first guy is equal to 2 over eta, but batch sharpness is still small, then we have like still convex optimization type analysis apply, and we have a stationary distribution. And this is exactly what Robbins, like when, let me say it, Robbins-Morrow type algorithm with wrong step size schedule. This is what a convex optimization person told me, or called how they called it, leads to. Still, so it's still like not surprising when and it's still not surprising, and this oscillation are like essentially noise driven. We really understand what those is. Like we have a very deep characterization of this oscillation. When those are both 2 over eta, then not anymore. Those are like curvature driven oscillation. And so this is like essentially like tells you also why this is the right generalization of edge of stability to the mini batch setting, right? And so like essentially we have like three quantities. One is like sharpness, is lambda max, or if you want, is like that quantity there. So it's like normalized along the step, the Hessian. And one is batch sharpness, in which normalized along the step our like the mini batch Hessian. And one is the gradient noise interaction, is like that other quantity that we get from the descent lemma on the full batch loss in expectation. And we see very consistently that small, like blue dots slow down here. This is lambda max. It stabilizes, but slow, but lower. Batch sharpness stabilizes, gets to 2 over eta with progressive sharpening and stabilizes there. Gradient noise interaction has no progressive sharpening, and whenever you start oscillating, it's 2 over eta, no matter what oscillations you have. So, and this is like the violet line there. Cool. So this is exactly what I said. And so essentially we have a characterization of in what sense edge of stochastic stability is the generalization of edge of stability. It was not in those like natural senses, and this was like the reason why I think, or at least the reason why for me it was difficult to come up with it, but it's the generalization of edge of stability from this point of view. And it's saying how is the generalization of edge of stability essentially like we also like solved like the missing implications, right? So we already said in what way locational convergence acclimates to parameter, that this is due to batch sharpness, and this is due to batch sharpness getting to the edge of its own stability. Like we didn't fully finish the picture about do optimization theory type analysis apply to SGD trajectory, and essentially like see the picture that we had on the previous slide. Now we completed them. Like convex optimization type convergence analysis just do not apply. Like the descent lemma does not apply. The descent lemma doesn't even apply, doesn't even explain the mini batch landscape trajectory, not even the full batch landscape. So it's like even strongly that the descent lemma does not apply. And also here, SGD does not decrease monotonically the loss, and gradient size increases. And like I proved it. We proved it that gradient size increases with our theorem. We say whenever batch sharpness is 2 over eta or right above, gradient size increases. Still, SGD is successful. So, except as for edge of stability, we said no. So essentially, we got it all. Those were our goals, and like we solved them. And you may say, hey, okay, but the implications, like very cool, but the implications are the same of edge of stability. In the next 10 minutes, I'm going to tell you not only. We have also more implications. Is everything clear so far? Cool. So what was edge of stochastic stability? A precise empirical description of the behavior of mini batch SGD. And white matter, now I kind of explain why it was a precise description of training dynamics and their instability, or their tendency to instability, or their lack thereof of instability. I also explain how this like SGD goes to flatter solution thing. Like we explain what's the machinery through which SGD goes to flatter solution, but we'll say a bit more in exactly 4 minutes about that. And like we also give key implication about what the mathematics has to do to explain deep learning trained with stochastic gradient descent. Cool. So like we gave implication number 1, which was like the implication essentially was the same implication at full batch edge of stability. Now I'm going to give you new implication. And one new implication, which is very key, I think, is about modeling SGD. So there has been plenty of work about, where does SGD goes? And I did part of this work, and this is how I started my PhD. And like, essentially, most of this work, it doesn't actually apply to SGD. And this is like, so it's like, this is like a further motivation for the mathematics of machine learning community. If you think about it, like, the way like edge of stochastic stability generalizes to edge of stability is that it is about quadratic instability, okay, not stability, instability, when we have random Hessians. So it's very key that we have essentially noise in the Hessians, because if we didn't have noise in the Hessians, then the threshold would be exactly lambda max equal to over eta, exactly as full batch gradient descent, right? So it's like it's very key that like the Hessians are random for like how explaining how SGD acclimates to parameter, and it's very key that the Hessians is random from the empirical observation of, for example, of Kesker et al. 2016. Yes. So as I was saying, why? Because like with stochastic gradients only, the threshold would be essentially lambda max equal to over eta anyways. So how do you model SGD? Well, many people model SGD as an SD. So you say, oh, okay, like when the step size is very small, like essentially have an SD, and let's see what the SD does. What's the point? It's like there have been many arguments for which this SD modeling doesn't work at doing certain things. I don't think it doesn't work at doing anything. I think it works. It works at telling you when you're on the stationary manifold where you go, sure. But it's like, if you think about it, SD modeling, or at least in the naive way, like it doesn't speak about Hessians, right? And also like when you model SGD as noise injected full batch gradient descent, that is not about the Hessian. You're injecting noise in the gradients, right? Mini batch SGD is about random Hessians. And we showed that the fact that it's about random Hessians is very key to in what way you have to generalize edge of stochastic stability, right? And in particular, we see that is like SD modeling and noise injected gradient descent actually go in different places qualitatively than mini batch SGD. Why? Why? Because essentially, if you look at the dots, not at the line for a second, the dots are orange, red, the lambda max for mini batch SGD. Orange, it's the labels bit wrong. It's like you understand why we're saying that in the paper, but like essentially orange is the lambda max for GD with noise injected, but noise injected also in the Hessian. And green and blue are the lambda max for GD with noise injected, but noise injected only in the gradients. And like essentially both isotropic noise, both isotropic noise and both like noise with the same covariance structure as mini batch SGD, they lead to lambda max equal to over eta if the noise is injected in the gradients. So this like answers a question that like many people was like say why is the case of something that many people always claim. There is like, oh, it's about the structure of the noise in SGD. It's not about the fact there is noise. Well, it's about the structure of the noise, but not about the structure of the covariance. It's about a deeper kind of structure of the noise. It's about the fact that noise is even in the Hessian, not just in the gradients. And this, like, to me, that I work on implicit regularization, maybe it's like the keyest implication of this work. And that says, like, SD limits may work in flat areas, just like they cannot deal with the old trajectory when the progressive sharpening is there. And it's like already like, okay, there are a lot of other arguments for which SD limits, in the naive way at least, may not work even in the flat area. So it's like, oh, it's like they work different than label noise and blah, blah, blah. So it's like we're not the first one to say that the noise is like in the naive way it's wrong. But we're saying, I think, one of the most qualitative differences that I know about so far about SD modeling or like gradient noise modeling and actual mini batch SGD. And we're also saying, hey, you can actually model SGD with gradient, with noise injection. Just inject this noise in the Hessian too. So it's like, this is like a very clear implication, right? And why? Because you reach instability in different locations. And let me conclude with like what do we know on lambda max? As I said, like the stabilization of lambda max, like lambda max increases, like stabilization of lambda max is about moving batch sharpness. It's not about moving lambda max. What we see is that lambda max increases at most as long as batch sharpness does. So this is a characterization we give. This is a fact about lambda max. The reason why I'm giving this fact is that like we don't have a characterization for where lambda max goes, and I think this is like probably like one of the keyest open problem empirically on this matter. Why? Because like the reason why I cared about this was like about the Hessian. So it's like telling you where the Hessian goes is like very key. Also because only the Hessian has been linked to generalization and also unlinked, if you want, from many paper, not other features. So it's like discussing the size of lambda max is very key. And like what we observe is the following: lambda max increases at most as long as batch sharpness does. From when batch sharpness reaches 2 over eta, lambda max just oscillates or decreases. It stops increasing, okay? And in particular, the level of stabilization of batch sharpness is stable and consistent per hyperparameters, but the one of lambda max is not. It's very path dependent. If I change hyperparameters, then it like restabilizes inconsistently, or if I initialize differently, it stabilizes inconsistently. So it's like if I take the same initialization but I scale it up, then stabilization is very different. Wait, for batch sharpness is not very different. So it's like it depends on initialization, implies it's not consistent with the hyperparameters. Also, so this is what I said, and also like we of course see the smaller batch size imply flatter minima, and I believe we push this observation further than previously done. So we show that there is a critical batch size mark, and this critical batch size is like an SGD GD crossover, and this critical batch size has been extensively seen in literature in other contexts, in context of stability and speed of convergence for neural networks. But essentially, that like we like clearly describe this thing. Unfortunately, we don't show like we could not figure out any power law, any law for the Hessian. Or better, we proved that there's no universal power law. So if you plot, here we're plotting on the on the top line, the stabilization level of lambda max. On the bottom line, the 2 over eta minus lambda max. Well, this is a log-log plot. If this thing was polynomial over in any sense, this would be a line. And this is not a line. So essentially, the log-log plot is not a line. It means that this gap is not explainable by a power law. So finding the size of the Hessian is still open. And the stabilization is a byproduct of edge of stochastic stability. So this is the end of it. Concluding, like we gave a precise and like to me surprising in many ways empirical description of the behavior of mini batch SGD on vision classification task with MSC, although it generalizes a bit, not as neatly. And essentially, like our goals were solved. It was like we said in what way location of convergence acclimates to hyperparameters, in what way the machinery inducing it is about stability, and that optimization theory type analysis do not apply to SGD trajectory. And also we made precise all these things. Just like how does it is like we give a description, it goes through progressive sharpenings, etc., etc. It's like we explain how SGD goes to flatter solution. Well, by batch sharpness going to 2 over eta, lambda max is secondary to that, still is an open problem. And we gave some key implications. So not only the optimization type key implication of edge of stability on full batch GD, yes, we generalize those, but also that like when you model SGD, you have to model it differently. You can model it. It's not that you cannot. You just cannot model it as noise injected GD. And that's pretty much it. So thank you so much from me and from Arseny. And I'm here as long as you like for any questions.
Yeah, thanks, Pierre, for this great talk. Let me first stop the recording.